The seafloor is rising. 300 miles off the Oregon coast, beneath nearly a mile of black Pacific water, the caldera of Axial Seamount is swelling. Pressure sensors bolted to the ocean floor are recording centimeters of uplift where there should be stillness. Seismographs are catching tremors, hundreds per day, each one a hairline fracture in rock that has held together for a decade. For 20 years, this volcano followed a rhythm. It inflated, it erupted, it deflated. The pattern was so reliable that scientists did something almost unheard of in volcanology. They made a prediction, and it worked. They called the 2015 eruption months in advance. Now the rhythm has broken. The inflation has surpassed the threshold that triggered every previous eruption. The caldera has swollen higher than it stood minutes before the last event, and nothing has happened. Or rather, something has happened that no one expected. The timeline collapsed, the models stopped working, and a series of distant earthquakes, thousands of miles away, began doing something to the magma chamber that the scientists are still struggling to explain. What changed beneath the seafloor? Why is the most predictable volcano on Earth suddenly the least predictable? And what happens if this eruption does not stay contained? Axial Seamount sits on the Juan de Fuca Ridge, a tectonic spreading center where new ocean crust is born. The ridge runs roughly north-south through the northeastern Pacific, separating the Pacific Plate from the Juan de Fuca Plate. Axial rises about 1,100 meters from the surrounding ridge, its summit crowned by a large rectangular caldera, an elongated depression left by prior collapses. At roughly 1,400 meters below sea level, it is permanently shrouded in cold, crushing darkness. It is also the most heavily instrumented submarine volcano on the planet. The National Science Foundation's Ocean Observatories initiative has threaded over 660 miles of fiber optic cable across the Juan de Fuca Plate, connecting more than 140 instruments directly to shore. Bottom pressure recorders, broadband seismometers, temperature probes, hydrothermal cameras, all of them transmitting data at the speed of light, 24 hours a day. No other underwater volcano has ever been watched this closely. And there is a reason for that, scrutiny. Axial is not merely active, it is relentlessly active. Geological mapping of summit lava flows has documented at least 50 eruptions over the past 800 years. Its lava is basaltic, hot, fluid, and fast-moving, flowing across the seafloor in glassy sheets and billowing pillows rather than detonating skyward. This is not Mount St. Helens. There is no ash column, no pyroclastic surge. The eruptions are quiet, almost silent, detectable only through instruments and the subtle biological blooms that follow, plumes of superheated water carrying billions of microbes from newly opened hydrothermal vents. But quiet does not mean insignificant. Axial was first detected in the 1970s by satellite altimetry and mapped by submersible dives through the 1980s. The scientific era of real-time monitoring opened in 1998 when 8,247 earthquakes rattled the seamount in 11 days, sending lava pouring from the caldera's southern flank in flows extending along 11 kilometers of its upper south rift zone. That eruption was detected in real time using the Navy's repurposed SOS-USA hydrophone array, a first for any underwater volcano. 13 years later, in April 2011, Axial erupted again. The caldera floor, which had been steadily rising as magma accumulated below, suddenly dropped by more than 2 meters as molten rock drained from the chamber. Large lava mounds appeared on the seafloor. The pattern held. 13 years of inflation, then failure.
Then came 2015. This eruption was different. Not in its mechanics, the lava was the same, the caldera collapse familiar, but in how it was anticipated. Researchers at Oregon State University, led by volcanologist Bill Chadwick, had been tracking the inflation curve for years. When the caldera reached roughly the same height it had achieved before the 1998 and 2011 events, a threshold of approximately 95% reinflation, Chadwick issued a forecast. He predicted the eruption months in advance. And within hours of the caldera beginning to deflate on April 24, nearly 8,000 earthquakes were recorded in a single day. Lava flooded the caldera. Data cables were buried. The seafloor dropped 2.4 meters in 3 days. It was a landmark moment. Axial Seamount became the first submarine volcano whose eruption had been successfully forecast based on ground deformation alone. But that success carried a hidden assumption that the pattern would continue. After the 2015 eruption, the caldera floor began to rise again. The cycle appeared to restart. Inflation climbed steadily through 2016, 2017, 2018. Then, gradually, it began to slow. By the summer of 2023, the uplift rate had dropped to nearly zero, barely a centimeter per year. The volcano seemed to be stalling. Then, in October 2023, something shifted. Inflation rates climbed again. Seismicity picked up. The instruments registered what Chadwick described as a fundamental change in the magma supply to the volcano. By December 2024, the caldera had reached 95% of its pre-2015 inflation level. Chadwick stood before the American Geophysical Union's annual meeting and offered a new forecast. Axial Seamount would erupt before the end of 2025. The world took notice. Social media posts about the volcano went viral, some garnering over 130,000 reactions in days. Headlines screamed that a massive underwater volcano was about to blow. But beneath the sensationalism, a subtler and more troubling story was unfolding. The inflation did not behave as expected. Here, a deeper look at the data reveals the scale of the problem. Bottom pressure recorders measure seafloor uplift with sub-centimeter precision. The key metric is differential pressure between a station at the caldera center, designated MJ03F, and a reference station east of the caldera, MJ03E. This differential measurement strips out ocean noise, tidal fluctuations, barometric changes, ocean currents, and isolates the true geophysical signal of volcanic deformation. By late 2024, that signal showed the caldera had inflated more than 20 centimeters since 2015, approximately twice the rate observed before previous eruptions. Seismicity was averaging 200 to 300 earthquakes per day, with occasional spikes past 1,000. The volcano appeared primed. Then the rate changed. By late April 2025, inflation had slowed again. Seismicity dropped to roughly 100 events per day, an order of magnitude below the 2,000 per day rate that preceded the 2015 eruption. The caldera had exceeded the 2015 threshold by nearly 10 centimeters, and yet no eruption followed. The volcano was swollen beyond any previously recorded safe limit, and it simply sat there. Chadwick wrote on his research blog, "It feels to me like Axial is just treading water lately." But the ocean was not finished with Axial Seamount. On July 29, 2025, at 23:24 UTC, a magnitude 8.8 earthquake struck off the Kamchatka Peninsula in eastern Russia. It was the most powerful earthquake recorded anywhere on Earth since the 2011 Tohoku event, tied for the 6th strongest in the history of modern seismology. The rupture tore across 600 kilometers of the Kuril-Kamchatka subduction zone, displacing the southern tip of the peninsula by more than a meter. 7 volcanoes in Kamchatka erupted in the aftermath, an occurrence not seen in nearly 300 years. 8 minutes and 23 seconds after the initial rupture, seismic waves reached Axial Seamount.
Hydrophones at the caldera recorded the arrival. The sound, when converted to audio, is a deep, rolling growl, the voice of the planet speaking across thousands of kilometers of ocean. The waves triggered automated eruption alerts at the University of Washington's cabled observatory. For a brief, tense interval, it appeared the eruption had begun. It had not, but the disturbance was real. The concept at work is called remote earthquake triggering, the idea that seismic waves from distant, powerful earthquakes can disturb magma chambers thousands of miles away, altering pressure regimes, clearing blocked pathways in subterranean dike networks, and effectively injecting stress into volcanic plumbing systems. The mechanism is documented in peer-reviewed literature but remains poorly constrained. Not all volcanoes respond.
Not all earthquakes trigger responses, but the correlation at axial, the automated alerts, the recorded waveforms, the timing was difficult to dismiss. And the Kamchatka event may not have been the only external influence. The Blanco fracture zone, a transformed fault system running directly south of axial along the ridge offset, is one of the most seismically active structures in the northeastern Pacific. It has produced multiple intense earthquake swarms over the decades, and based on what we know about stress transfer in oceanic lithosphere, any significant seismic energy release this close to the seamount could plausibly redistribute stress within axial's shallow plumbing system. The fracture zone lies close enough that mechanical coupling between the two systems is not theoretical, it is geometric fact. Each regional seismic event, based on the available data, could be interpreted as a kind of external pressure injection into a system already near failure. The pattern resembled less a single internal countdown and more a series of nudges from the broader tectonic environment. This raises a question the models were never built to answer. Axial's forecasting framework rested on a single assumption, that eruptions are driven by internal magma accumulation. The caldera inflates, reaches a threshold, and fails. But if external seismic events can alter that threshold, if distant earthquakes can force-feed magma into the chamber or clear blocked pathways in the dike network, then the entire predictive model is incomplete. Beneath axial seamount lies a labyrinth. The magma does not reside in a single tidy chamber. It occupies a network of sills and dikes, thin horizontal and vertical intrusions of molten rock threaded through the crust like veins. These structures connect the seamount to the broader Juan de Fuca Ridge system, which stretches for hundreds of kilometers in both directions. Axial is not an isolated point. It is a node in a larger magmatic network, fed from below by the Cobb hotspot, an anomalously hot mantle material that has been interacting with the ridge for at least 500,000 years. When seismic waves pass through this network, they can, in principle, shake loose congealed magma, reopen sealed fractures, and redistribute pressure across dozens of interconnected pathways. The effect would be less like triggering an explosion and more like unclogging a pipe. Under this interpretation, the volcano does not erupt because a single threshold is crossed. It erupts because the entire network reaches a state of collective failure. This is what makes the current situation difficult to model. The Juan de Fuca plate, born at the ridge where axial sits, drifts eastward at roughly 4 centimeters per year. As it moves, it cools, densifies, and eventually plunges beneath the North American plate along the Cascadia subduction zone, a 1,000-kilometer locked fault stretching from northern Vancouver Island to Cape Mendocino, California. This is the fault that produced the magnitude 9.0 earthquake of January 1700, the event recorded in Japanese tsunami logs and Native American oral histories. The fault has been locked and loading stress for over 3 centuries. The connection between axial seamount and Cascadia is tectonic. They share the same plate. Stress changes on the ridge propagate eastward through the crust. Based on what we understand about stress transfer in oceanic plates, a large eruption at axial, particularly one involving lateral dike propagation along the ridge, could theoretically alter the stress field on the subduction interface. Not enough to trigger a megathrust earthquake directly. No peer-reviewed study has demonstrated a direct causal link between an axial eruption and Cascadia slip, but perhaps enough to modestly change the loading conditions on a fault already accumulating centuries of strain. The Cascade volcanoes, Mount Rainier, Mount Hood, Mount St. Helens, Mount Shasta, are themselves products of the same subduction process that consumes the Juan de Fuca plate. The magma that feeds them originates in the mantle wedge above the descending slab, the same slab that was once seafloor at the ridge. This shared tectonic architecture does not prove a direct connection, but it implies that activity at one point in the system could, over geological timescales, influence conditions elsewhere.
Sediment cores pulled from the ocean floor near axial tell a parallel story.
Turbidite layers, deposits left by underwater landslides typically triggered by earthquakes, alternate with volcanic ash beds in a repeating pattern stretching back over 10,000 years. The record suggests that eruptions and great earthquakes have occurred within the same geological windows, not necessarily simultaneously, but close enough in time to imply a shared tectonic rhythm. Whether this represents direct causation or simply the natural cadence of a restless plate boundary remains an open question among researchers. Whether the current inflation episode at Axial is a prelude to one of those cycles is unknown. The eruption, when it comes, will not be cinematic in the way most people imagine volcanism. There will be no mushroom cloud, no fiery explosion breaking the ocean's surface. A mile of cold seawater will press down on the erupting fissures, suppressing gas expansion and keeping the lava contained to the seafloor. The magma beneath Axial contains fewer dissolved gases than magma erupted on land, making submarine eruptions inherently less violent. What happens is slower, quieter, and in some ways stranger. Magma will push through cracks in the caldera floor, spreading outward in lobes of incandescent basalt that freeze almost instantly on contact with near-freezing water, forming pillow structures, bulbous, glassy shapes that look like stacked cushions. The caldera floor will drop as the chamber drains. Fissures may open along the ridge flanks, extending up to 25 miles from the summit. The eruption could continue for about a month, gradually reshaping the seafloor. But a fisherman on a boat directly above the caldera would feel nothing. A woman in Astoria, Oregon, 300 miles to the east, would not know it happened unless she checked the news. As Chadwick himself told reporters, for the size of eruptions seen in the last 20 years, if you were on top of it on a boat, you would never know it. The instruments would know. Every sensor on the cabled array would register the event in real time. The sharp acceleration of earthquakes, the sudden deflation of the pressure sensors, the temperature spike at hydrothermal vents, the milky plumes of microbial blooms billowing from fresh fissures into the dark water. Scientists in labs at the University of Washington and Oregon State would watch the eruption unfold on their screens, minute by minute, the first people in history to witness a mid-ocean ridge eruption from start to finish through a cabled observatory. That is, if the instruments are still there. The administration proposed an 80% cut to the National Science Foundation program that funds the Ocean Observatories Initiative. The cabled array, the only real-time monitoring system capable of watching Axial, secured enough funding to operate through the summer of 2026. Beyond that, the future is uncertain. The most monitored submarine volcano on Earth could go dark at the precise moment it becomes most scientifically valuable. The latest data, updated through January 2026, show that Axial continues to inflate. The caldera now sits roughly 10 centimeters above its pre-2015 level. Seismicity remains active, but below the threshold scientists believe is necessary to trigger an eruption, approximately 500 earthquakes per day sustained over weeks, based on what was observed before the 2015 event. The current forecast, revised at the December 2025 AGU meeting, places the eruption window at mid to late 2026, but the researchers themselves acknowledge that the variable inflation rates have repeatedly confounded their predictions. A new physics-based forecasting experiment, launched in November 2025 by researchers from Uppsala University, ETH Zurich, Oregon State, and the University of Washington, is attempting to predict the eruption using mathematical models of structural failure, the same kind used to forecast landslides and glacial collapses. Their forecasts are cryptographically sealed and archived. They will only be opened after the eruption occurs, a radical transparency designed to eliminate hindsight bias. The first sealed forecast was issued on November 8, 2025, the second on December 22nd, the third on January 30, 2026. No one outside the experiment knows what they say. What is known is this: Axial Seamount has exceeded the inflation level that preceded every eruption in its recorded history. The pattern that made it the most reliably forecast volcano on Earth no longer holds. External seismic events from across the Pacific appear to be interacting with its magma system in ways that current models cannot fully account for. The monitoring network that watches it faces an uncertain future.
and beneath the cold darkness of the northeastern Pacific, the caldera continues to rise. The sealed forecasts sit in their encrypted files. The pressure sensors transmit their readings to shore. The seismographs record every tremor, every fracture, every whisper of movement in the rock below. Somewhere in that stream of data, the answer exists, the exact moment when the crust will finally give way. The instruments are listening, but no one knows how much longer they will be allowed to be.